So good morning. Today we have Jong-Hoon Lee from University of Korea Integrated Bioelectronics Lab to give a talk about high conductive and flexible sensor integrated with personal device for practical biosignal measurement and applications. Without further ado, you have the floor.
Okay, thank you for introductions. Today, I'm going to announce to you the topic I study at the university. I have fabricated highly conductive and flexible sensors and developed the wearable biosensing device and conducted a study about the healthcare applications with the biosignals. So I'm going to present a selection of topics that match the theme of my summer internship. So the title of topic is highly conductive and flexible sensor integrated with personal device for practical biosignal measurements and applications. We generally measure the electrical biosignals on our skin. The source of the electrical potential is generated by the neurons and cells activity, and once the action potential exceeds the certain threshold voltages, it flows through the ion channels of our body. So our body is inhomogeneous volume conductor, and if the ion fluxes can create the electrical potential on the surface of our body. So we can measure the summation of action potential generated by the neurons on our skin. We call these biosignals. As you can see here, we can measure the loss of vital signs on our skin. Through the measurements of the biosignals, we can easily determine whether or not each organ is normally performed. By the way, we call each biosignals very shortly. The brain signal is electroencephalogram, we call it EEG, and the heart signal is electrocardiogram, we call it ECG, and the muscle signal is electromyogram, and we call it EMG, and eye signal is electrooculogram, we call it EOG, something like that. So among these type of many biosignals, the EEG and ECG is the very important biosignals of our body related to our life. So I'm going to focus on to present with the EEG signal and the EEG signal measurements device. As I mentioned before, the EEG signal is one of the most important biosignals of our body. So in the past, the EEG signal is normally used in the clinical diagnosis areas, but as the technology developed, it has been used in lots of research areas such as ubiquitous healthcare, brain-computer interface, and even social applications areas by using the general public. So this biosignal is more and more becoming popular among the general public. Despite the interest of the general public, there are several drawbacks to the conventional EEG recording systems. There are some limitations due to the characteristic of the EEG signals coming from the head. So the conventional EEG recording system have lots of electrodes, limitation on mobility, and pace problem, and even currently developed wearable EEG sensors have obtrusive wearing. So nobody wants to wear this kind of devices in their daily life. So I think new paradigm of EEG device will be highly required for anyone to use in their everyday life. So I have developed new paradigm of wearable head-on device, such as the EEG device, with the 5 different visions. The new device must be simple using and unobtrusive wearing, wireless recording, and also comfortable wearing, and even biocomfortable for users. In the case of the body-worn sensor that is attached to our bodies, it is more focused on the functionality without considering appearance. That is because the body-worn sensor are able to hide under our clothes. However, in the case of the head-worn sensor, it is not able to hide under our clothes. That is because our face and head is generally exposed. So the form factor of wearable head-worn device is very, very important. So I thought of the wearable device concept of combining EEG sensor with a personal device, such as the head-worn personal device. Among the lots of personal device, I choose earphone and eyeglasses form factor to measure the EEG of the wearable sensor. So it has some advantages about user-friendly and easy to wear and unobtrusive wearing in our daily life. So with these advantages, we can widely use this kind of wearable device in our daily applications in healthcare areas such as BCI and human-machine interface and brain-computer interface. So the first topic to introduce is Inear EEG earphone concept. Nowadays, you can easily see those who wear their earphones in all the time. So they are using it during studying, reading a book, and even doing sports. So the earphone have become a necessary item of our nowadays. So the earphone is kind of best form factor to wear on our head without any efforts. By the way, the brain signal can be detected in our ears because the brain signal spread out radially in the brain. So I combine these two different ideas together to develop a wearable device to measure the EEG signal in the ear. Since the EEG signal's amplitude is quite small, so the sensing material is highly conductive and flexible. So I developed the silver nanowires CNT-PDMS by mixing silver nanowires and carbon nanotubes, which are highly conductive materials, with biocomfortable PDMS elastomers.
What is PDMS?
It's kind of a rubber, so it's a kind of a elastomer, and the characteristic is quite soft and flexible, and
it's conductive?
Yeah, it's a kind of silicone.
Silicone.
Yes. So I made this silver nanowire CNT-PDMS composite, and the characteristic and the carbon nanotubes provides the conformal connectivity, conductive connectivity in the elastomers, and the silver nanowire dramatically improves the conductivities. So here shows some result of the electrical property characteristic of silver nanowire CNT-PDMS composite. And especially on the C figures, it shows the skin and electrodes contact impedance. The result shows that silver nanowire CNT-PDMS contact impedance is comparable to the commercial wet type of silver chloride electrodes. So I use these highly conductive sensing materials with the EEG sensing device electrodes.
Question?
Yes?
Why did you use both carbon nanotubes and silver?
Oh, yes.
One's better than the other. Why would you use?
Actually, just using the carbon nanotubes, it has a conductivity, but it's not that high for measuring the EEG signals. So I I put the silver nanowires a little bit, it improves dramatically the conductivity. So it can...
But if you take out the carbon, it's not as good. You have to have both.
Yes, both. Yes.
Okay.
So the carbon nanotubes...
Explain the aspect ratio to Patrick of the carbon nanotubes. That will maybe help him understand
I see.
why.
On its orientation and aspect.
We'll let him answer the question.
Yes, the diameter of CNT carbon nanotubes is about 20 to 30 nanometers, and the long length is 200 micrometers. So it's quite long, and aspect ratio is quite large. So it can connect the conductivity inside the elastomers. Yes. So here shows the appearance and the components of Inear EEG earphone. As you can see here, the Inear EEG earphone consists of two parts. One is the silver nanowire CNT PDMS-based Inear Cap Sensor, and the other is EEG earphone, which is the measuring system. So the EEG Cap Sensor is made by attaching the conductive interconnection layer with the silver nanowire CNT PDMS composite together on the memory foam. And this Inear Cap Sensor is also designed plug and plug out. Is replaceable. So the Inear Cap, the EEG signal is measured by with the Inear Cap Sensor and transmitted to the metal layer of the frame of EEG earphone and transfer to the circuit system through the signal lines. Also, the mechanical modulus of Inear Cap Sensor is much lower than that of the bulk polymers. So this result shows that Inear Cap Sensor provides comfort wearing of Inear EEG earphone. I also did the comfort study of the Inear Cap Sensor. The finite element analysis simulation was conducted to study degree of the comfort when wearing the Inear EEG earphone of our ears. So I carefully designed the model of ears and each part of the Inear Cap Sensor. And I also did the study about the applied pressures when the Inear Cap Sensor come into our ears. As a result, the applied pressure is lower than enough to cause the discomfort, and the electrical resistance change of the sensor did not change significantly. So with this result, I indirectly learned that this Inear Cap Sensor is suitable for measuring and wearing of our ears. Here shows the EEG recording system. The recording system is one-channel system and consists of 3 electrodes, source, reference, and ground. So the measured EEG signal is transmitted to the wirelessly to the smart devices such as smartphone and laptops through the analog filters and amplification systems.
So you do, can I go back?
Yes.
So you do differential amplification. Where is the reference? They both are in the Inear electrode.
Yes.
Okay.
So the sensor position optimization test was performed to optimize the sensor position inside the ear. So I carefully divide each experiments into the several groups. So, and then finally found the best position of the Inear Cap Sensor of the electrodes. So the best optimized position is when the source electrode is upward of the right earphone, and the reference electrode is upward, and ground electrode is downward of the left earphones. So with these optimized sensor positions, I measured some EEG signals of the feasibility test. The feasibility test was performed to evaluate the developed device. So 3 feasibility tests was performed. Two is related to the visual stimulation, and 1 is related to the auditory stimulations. The first feasibility test was alpha rhythm detection test. In general, people are in rest state or close their eyes. The 8 to 14 hertz of the alpha rhythm is highly expressed in our brain. So with this biological mechanism, I measured the alpha rhythm by closing our eyes. So for the experiment setup, we instructed the subject to open their eyes before 60 seconds and close their eyes another 60 seconds. So as you can see at the A figures, you can easily figure out the signal differences before and after 60 seconds. And also on the B figures, the spectrogram results. The x-axis shows the time and y-axis shows the frequency. So on these figures, you can also figure out the alpha rhythm near the 10 hertz after 60 seconds. Although the amplitude of the in-ear EEG earphones is lower than that of a commercial system, which is attached on our head, but we successfully measured the alpha rhythm with the in-ear EEG earphone.
So please clarify. On the 2 spectrograms,
Yes.
on the right we have a signal from a cap,
Yes.
and on the left is your.
Yes.
So you still can see, yes.
Yes. Yes. But the amplitude is quite different. Yes. The second and third feasibility test was related to the evoked potential. So the evoked potential is brain response against the external stimulation. So the second is about visual stimulation, and third is about auditory stimulations. We also successfully can measure the both visually and auditory stimulations brain activities. For the practical application of our in-ear EEG earphone, we try to measure the drowsiness state of people. So we usually do the concentration work, such as studying and reading a book and reading papers while wearing our earphones. So, and we often fall asleep and getting a drowsy state without our knowing. So here is our motivation of these applications, that if the earphone can awake the people during the drowsy state, the work efficiency will be improved. So for the generally, when the people are in the drowsy state, the 4 to 7 hertz of theta band and 8 to 14 hertz of the alpha band is getting stronger. So with this biological mechanism, we try to measure the drowsy state. So for the experiment setup, we had a repetitive clicking task on the subject who was limited their sleep before the previous day, driving them more drowsy state. So we instructed the subject to click a button when the when the black sign changes the red sign. The sign changes randomly. So during the experiments, I measured the clicking reaction times and name on the errors when the clicking reaction time exceeds the certain threshold time. So during the experiments, I judged the drowsy state of the people when the number of errors going high. So during the drowsiness state, I successfully measured the change of the EEG signals, the alpha band and theta bands getting stronger. So as a result, this is the kind of a very simple version of applications, but we successfully measured the drowsiness state with the Inear EEG earphone. So this is a very promising wearable EEG device for the practical use in our daily life. The second topic is smart eyeglasses concept. As you know, the eyeglass is so familiar to us, so it is no exaggeration to say that 1/3 of populations using the eyeglasses. By the way, it's very surprisingly, more than 87% of the human sensory input can be obtained by our head, such as the 5 senses. So we can measure the variety of biometric informations, such as brain signals and eye signals and the other 5 senses with several sensors at our head. And we can use this kind of biometric informations to use the command signal to manipulate the machines. So on this topic, I'm going to show you the human-machine interface applications with some sensors attached on the eyeglasses form factor. Form factors. So this figure shows the appearance and the components of multifunctional smart electronic eyeglasses. So as you can see here, some sensors and systems are embedded in the eyeglasses. So the frame of eyeglasses is customizable for users and made by using 3D printing technologies. And biosignal measurement sensors are attached 5 different places to measure the EEG signal and EOG signals. And the sensing material is similar to the previous reported one. So it is carbon nanotube-based elastomers. And the color changeable display is for the protect our eyes from the UV radiations actively. So we apply some color changeable materials on the lens of eyeglasses. And the other commercial sensor and wireless system is embedded in the frame of eyeglasses. For the material of color changeable glass lens, we used the previously reported electrochromic gel. The electrochromic gel can change their colors by oxidation and reduction reactions in the ionic components of electrochromic gel by applying certain voltages to the electrochromic gel. The characteristic of this gel is transparent and freestandable, that we can easily apply these materials to the lens of our glasses. And then when the certain or more intensity of UV is detected by UV sensor, the systems, the microcontroller actively apply the voltages to the electrochromic gel to change their colors. So this device can change their colors for the eyeglasses to the sunglasses. And the reverse reaction can be available.
Just a question. So this is a film which goes over the optical lenses.
Yes.
Okay.
Mm-hmm. So this is the result of smart real image of the smart electronic eyeglasses. So inside shows the sunglasses mode, and some sensors and systems are embedded in the eyeglasses. So the biosignal measurement electrodes are embedded here and very conformally connect to our bodies, just wearing the eyeglasses. And the commercial sensor and electronic recording systems are embedded the body of the eyeglasses. So various type of biometric informations can measured with the smart monitoring systems. I will show this slide. I will show the human-machine interface applications with commercial components. So first is the color changeable lens operation, and second is motion detection with the acceleration sensor. So on the first human-machine interface applications, we can measure the ambient UV intensity with the UV sensor of our system. And when the UV intensity is detected by the sensor, the system actively applies the voltages to operate the sunglasses. So on the, especially on the E graph, E figures, when the UV light is turned on, the eyeglasses change the sunglasses directly, and the transmittance of sunglasses with the UV wavelengths is extremely low. So this figure, this result shows that the sunglasses mode can actually protect our eyes from the UV radiations. So this kind of applications can be used for our daily life and also for the using the displays with the AR and VR technologies. The second is motion detection. So we're combining the three different components of each axis data together, and we figure out the different motion differences patterns, such as working and running and sit down and stand up like that. So we recognize the emergency situations such as the falling down. So these applications can be used for the patient who needs help when they're falling down. These wearable devices can contact their families with the smartphone.
And you use it just a 3-axis accelerometer, no
Yes.
gyro, no compass, just...
Yes, no.
Okay.
Here shows the human-machine interface with the brain activity. We also successfully measure the brain activities with such as alpha rhythms, and we apply these technologies with the direction controls. So for the human-machine applications with the EEG signals, we had a direction control that actually generally on the humans, when see the certain frequency of the visual stimulations, the brain modulated with the same frequency of the visual stimulations, and we can detect the peak of the stimulation that we call this SSVP, visually stimulation, steady state visually evoked potentials. So we use this technology when the subjects want to select the right directions. The subjects stared at for a while for the 14 hertz. So if the subject shows these stimulations, their brain modulates with the 14 hertz. So we can measure the 14 hertz of the peak with the frequency areas, and we use this peak signal with the command signal for the direction control. So this kind of technology is quite common in the brain-computer interface areas, and we also demo with this kind of technology with the eyeglasses. So this is useful for the patients who can moving their limbs freely, And also it can be useful for the AR or VR technologies. This shows the human-machine interface with the eyeglasses, eye activities, the EOG signals. The EOG signal is quite clear signals, such as our heart activities. So this EOG signal has much advantages to use as a command signal to manipulate the machines. So the saccadic eye movements, which is one of the EOG signals, the saccadic eye movements is electrical signal that occurs when the eyes moves quickly left to right and right to left. So as you can see here, the amplitude and shape of the saccadic eye movements is depending on the angles, eye movements angles, and directions. So as you can see here, you can figure out the different shape of the left signal and the right signals. So we use these technologies. We measure each saccadic eye movement signals up to 40 degrees by the 10 degrees, and we classify it. So with this result, we apply this technology to the very basic game controls, the Tetris block movements. So when the subjects move their eyes 20 degrees, the block moves one step, and 40 degrees, it moves 2 steps. So here shows the EOG signals, and we control the blocks in real time, something like that. So this is the kind of very basic applications with the EOG signals, but we chose the possibility with the EOG signals to manipulate the machines by just wearing our eyeglasses and moving our eyes. So, conclusion, I have introduced the promising personalized head-worn devices for practical healthcare applications. The first is the Inear EEG phone, and second is multifunctional smart eyeglasses. Both devices are combining biosignal measurement sensors with the personal device. And the characteristic of this device is 3D printing and customizable design for anyone, and very simple and convenient and comfort to using for anyone to use. And the appearance is very reasonable for in daily life using. Also, many kinds of health information can be detected from the head. The system is fully wearable due to the wireless system. So I think these two head-worn biosignal devices is promising for healthcare areas, for PCI and HMI areas. Before finish the presentation, I'm gonna introduce briefly for my research topic of summer internship. I'm currently trying to fabricating the wearable stress detector with biosignals. We usually feel the stressful, but we just thinking about it's not a big deal. But the chronic stress can be a serious disease. So our body feels some stress. The body make some symptoms like anxiety, anger, and headache, something like that. So, and then according to some surveys, more than 75% of the US adults report that they have at least one symptoms of the stress. And more surprisingly, more than 85% of disease are related to the stress. So almost all kinds of disease are related to our stress. So it is very important to know and manage our individual stress level. So the stress level detector is highly required in future daily life. So according to the previous reported papers, there are some kinds of biosignals related to our stress level. So among those biosignals, I choose three biosignals: the EEG and ECG and the GSR, the skin conductance. That's because these three biosignals are deeply related to our healthy life and also the stress level. So I tried to measure the fully wearable Inear biometric stress detector, and I used the form factor as a earphone type, as I mentioned above. And especially I motivate with the sporty type of commercial earphone. That's because this type of earphone have a lots of contact areas of our head, and it can stably fix this device on our head. So I use this form factor, and some of the biosignal measurements electrodes are attached near the ear and our neck. So ultimately, our research goal is to alert the users when the user have a high stress level and drives them to rest and release the stress. So we are now working with the Kai paper, and actually currently our in progress is just trying to acquiring the biosignals, the EEG and ECG and GSR, and actually we need some machine learning technologies. So I would like to collaborate with the expert of the machine learning and familiar to biosignal signal processing. So please contact me, anyone who interested in this topic, with this email address. Yes. Thank you for listening. Yeah.
Questions, dear colleagues? Well, we think, so going back to the Inear electrodes.
Oh, okay.
You did the electronics, right?
Yes.
Tell me a little bit about the analog part and what kind of A to D converter you use it. What is the gain of that differential amplifier?
Gain. Oh, yes. The gain is about 3,000 gain is applied for measuring the EEG signals. I use the operation amplifier with the amplifications. Yes.
What is the bandwidth of the bandpass filter?
Bandpass filter is a third degree of the Butterworth bandpass filters. So it is 1 Hz to 35 Hz, the bandpass area.
1 to 35 third order Butterworth for both low pass, and for high pass you have separate third order Butterworth.
Yes, yes.
Nice. Mm-hmm. So your input signal is in the magnitude of 10 microvolts.
Yes, yes.
With 3000 it goes 300 millivolts.
Yes, yes.
Okay, this is already enough good for the A to D converter.
Yes.
Could you go to the next slide? I'm interested to know where the census and the references are.
Next slide. Right.
Yeah.
Oh, yes. So I did some sensor position test. So for the ground electrodes and reference electrodes, I fixed the upward and downwards, and I changed each direction of source electrodes like that. So as I found that when for this position is very best for detect EEG inside the ear.
Have you collected experiments when the subjects move their eyes?
Oh, yes, yes. The eyes movements is detected inside the EEG signals, but it can reduce, reject with signal processing.
Yes, I understand that, but your configuration of where the electrodes are is also optimal for EOG.
Oh,
So you ended up getting a lot of EOG just because of the configuration.
Oh, yes, yes.
Because you're picking exactly that dipole.
Oh, yes. As you mentioned, the EOG, some of EOG is detected inside the EEG signals, but we can reject that kind of EOG signals inside the EEG signals. Yeah.
And the same question about ECG. So in your last design, you have your in-ear electrodes for EEG,
Yes.
and your ECG electrodes are here.
Yes.
I'm pretty sure you'll see plenty of ECG in the EEG electrodes. How you'll deal with that?
Actually, I separate the measuring system of the. I use the two band pass filters with the ECG and EEGs. So I separately measure the analog signals to microcontroller. So it's not that measured.
ECG is a very broadband signal compared to EEG. Pretty
Yes,
much
yes.
the bandwidth of the electrocardiographic signal is all over the place of the EEG.
Actually,
We
I
have the same dipole here, which basically the heart activity is projected on this line.
actually for my experiments, I cannot find the ECG signals inside the ear. So
Interesting.
yes, that would be not that problem for
That's
me.
why we moved them down here, because we couldn't find it in the ear. So even with filtering, we couldn't parse it out. So which is contrary to what you told me 2 weeks ago,
Yep.
a month
Yep.
ago, where you said it was going to be so strong it was going to drown everything out. We had just the opposite challenge. So maybe so this is an area where maybe we have some learnings to do, or there needs to be some deep signal processing.
Also separate out MEG too. So in magnetometers, you would pick it up anywhere, but EEG, that's not necessarily the case. But in a more general sense, there's no reason why you only have one sensor on the right. Since you have this 2-channel on the left, you should just do it a generic 2x2, and then just work out what type of signals that you actually want.
That's fair.
And then go from there. You don't have to say that's a reference and ground. Because your sensory profile would be different. You can treat that as a beamformer.
That's fair.
So, any more questions, colleagues?
Does the earwax, is that an insulator or a conductor? I mean, does that make it signal degrade over time if you wear this all day?
Actually, the long-term measurements experiments is not conducted. That I think for the ear measurements, there's some generate some heat from inside our body. So I'm not sure about that, but the electrodes is very dry type of electrodes. So when the sweat is exposed by our skin, it doesn't matter to measure the signals. Yeah.
It's also culture dependent. So depending on ethnicity,
The conductivity,
the form of the UX is different.
the density, or the viscosity?
Yeah, Asian tends to have more
Closed or open
solid, and Caucasian is more liquid.
And there's the 5th percentile Shrek where you hold camp.
Oh yes.
Yep, I just have a question regarding the SSVP stimulation. So, did you display it on the glasses or just on?
Yes.
your
On
screen? And on
laptop
your
and-
averaging for the PST, how much was it? How long?
Oh, it's we measure the 30 seconds. Yeah. So is that
So it's one subject, it's one trial, 30 seconds average.
yes. It's quite long. Yeah. Yes.
But your eyes are allowed to move, right?
Yeah.
So it's basically an overt concentrated in floating currents, and that's
Yes,
why you don't
yes,
see
yes.
any other frequencies.
Yes.
More questions?
I guess.
Oh, yes.
Yeah, I see the mechanical and sensor setup, but do you have results at this point, or this
Oh.
is kind of a mid?
Results?
Yeah, I mean, are you able to classify, so eyes open, closed, like blinks? Can you do blinks? I mean, I'm trying to see what's the limit of what you can see. On the previous slides, you were seeing eye blinks.
Yes.
And, some other things. If you have
For these experiments, we instructed subjects to stay their eyes So we reject the eye clicking and blinking like that. So for our measurements. Yeah.
Okay. And do you have a place where you want this to end up? Like, are you trying to drive the signal processing to the point where you can pick up more things, or are you kind of finished with your study?
We talked about
do
that
that.
offline.
Yeah.
Cool.
More questions? If not, let's thank our speaker again.
Thank you.